Okay, so we're working with a construct that is called the Leontiff input-output model. Um, Essentially, the way that these things work is you end up with a matrix that describes the world. Okay, and in the world that we're going to describe here, or sorry, doesn't describe the world, it describes a local economy. And in my local economy here, I'm going to say I have three major producers: an electric producer, a water producer, and a coal producer. Okay, and this is the output, and this is the input. Okay, so what we're going to say here is that in order to produce 1 unit of electricity, we're going to have to consume half a dollar of electricity, or 50%. Okay, so if I'm going to produce $1 of electricity, it's going to cost me half a dollar. To produce $1's worth of water, I'm going to consume 60 cents of water. And in order to produce a unit of coal, I am going to consume 50 cents of coal. Okay, so the next step in this is that in order to produce a unit of water, right? Or sorry, in order to produce a unit of electricity, it's going to cost me 25 cents of water. And in order to produce a unit of electricity, it's going to cost me 25 cents of coal. In order to produce $1's worth of water, it's going to cost me 10 cents of electricity and no coal. So like we got a pumping cost there, right? If I'm going to produce $1's worth of coal, it's going to cost me 20 cents of electricity and 15 cents of water. So this describes my local economy. This is what we call an I-O, or an input-output matrix. Okay, so I'm going to use this, and that's fine. It's a nice closed system. It describes what's happening within the economy. But usually we try to use these problems, these matrices, to try to deal with how much do I have to input into, how much do I have to manufacture, or how much of each thing do I have to have in production in order to meet some external demand. So my local economy is actually going to interact with a world, and that world is going to make a demand upon that local economy, which means I have to know what rates do I have to produce in order to meet that external demand. Okay, so let's say I have an open system and my input-output matrix has 3 products in it. Okay, so we'll keep it simple. And in order to produce a unit of A, I have to have 10 cents. So in order to produce basically $1's worth of A, I have to have 10 cents of A coming back. I have to consume 15 cents of B and 23 cents of C. In order to produce product B, I have to have 43 cents of A, no cents of B, and 3 cents of C. And in order to produce product C, I need none of A, 37 cents of B, and 2 cents of C. Now, I have an external demand. My external demand tells me that I want $20,000 of product A, $30,000 of product B, and $25,000 of product C. So I put that in a column matrix. So what I want is some matrix X that tells me the rate of production for product A, the product B, and product C. How much money do I have to put into the production of these things in order to produce that surplus, to meet that external demand? Well, if you think about this, X1 should equal, so if I call this like D11, D12, D13, should be D11 times x1, because that's what's coming back to it, plus D12 times x2, right, because 0.43 of x2, plus D13 of x3, plus my external demand of item 1. So we're going to call this E1, E2, E3. Okay, so I'm going to get two other equations. I'm going to get one for x2, which is D21x2 plus D22x2 plus D23x3 plus E2. X3 should be D31x1. Sorry, this should be an x1 here. Plus D32x2 plus D33x3 plus E3. Okay, so what I want here is each unit of x1, right? So the number of units of x1 should equal how much, well, should equal what I spend from each of these three plus the surplus, right? So ultimately, if I look at this, I can rewrite this as x is equal to dx plus e, right? Because if I multiply this times this, I'm going to get this mess in the middle. E is going to be down here and x is over here. Well, I can solve this equation for x. X minus dx is equal to e. The identity minus d times x is equal to e. X should equal the identity minus d times e inverse, right? So I'm bringing it to the other side. I have to take the inverse. Okay, so let's look at how that plays out in this problem, right? So I'm going to drop that in here. Oops. All right, so let's start with our givens again. Our I/O matrix again was 0.1, 0.43, 0, 0.15, 0, 0.37, 0.23, 0.03, 0.02, and our external demand was 20,000, 30,000, 25,000. And we just established using a little bit of algebra that x has to be the identity minus d inverse times e. So the first thing I need is the identity minus d. Okay, so let's see, that's going to be 1 minus 0.1, which is 0.9, 1 minus 0.43, or 0 minus 0.3 is going to be negative 0.43, 0 minus 0 is 0, negative 0.15, 1, negative 0.37, sorry about that, negative 0.23, negative 0.03, and 1 minus 0.2 is 0.98. Okay, if I drop that into MATLAB and I get an inverse, I'm going to end up with 1.25, 0.55, 0.21, 0.30, 1.14, 0.43, 0.30, 0.16, 1.08, and I multiply that by my external demand. And that gives me back a matrix of 46,750, 50,000, 950, 37,800. So that means that if I drop this much money into each of these three segments of the economy, I will not only meet the internal demand of the economy, but will have this in surplus, okay, which I can export and now sell, and then hopefully bring back a profit and keep things going. So like I'm putting money in, exporting, hopefully selling at a markup, and then coming back. And I've supported the local economy and met the external demand if I produce at these values. All right, so that's a basic idea of Leontiff I-O systems, and we will work with them in class.